This is part one of a two-part series of videos where we're going to cover cylindrical coordinates and spherical coordinates. So if you're keeping up with the class, this is going to be section 11.7 from our textbook. So in this section, we're going to study two different ways of representing points and then surfaces in space. We're going to start with cylindrical coordinates in this video, like I said, and then spherical coordinates in the next video. So in a cylindrical coordinate system, a point P is represented by an ordered triple, r, theta, and z, where r theta is the polar representation of the projection of the point in the xy plane, and z is a directed distance from r theta to P. Let's try to make some sense of that. Just reading that paragraph, it might not be very intuitive, it might not make a lot of sense. I think we can explore this a little bit further. All right. So here's the deal. If we think about an xy coordinate plane, and we know that we're going to be working in space, so let's draw it as if we plan on working it in space. If we pick a point in our x, y coordinate system, let's go ahead and let's draw a point somewhere. And we could think of our point as having an x-coordinate and a y-coordinate. Eventually it's going to have a z-coordinate, so I'm going to leave a little bit of room there to draw the z-coordinate, but for now it just has an x-coordinate and a y-coordinate. Right? That's one way that we can represent that point in the plane. Right? Another way that we can represent the point in the plane, though, is by thinking about its polar representation. So we can now imagine not just referring to that point as an x-coordinate and a y-coordinate, but now we can imagine talking about the distance that that point is from the origin. We'll call this distance r, and the angle that's formed in standard position. And remember, angles in standard position always stem from the positive x-axis. Right? So we can also describe that point, that x, y, as a point that has an r value, or a distance from the center, or the origin, and an angle theta. Right? And we do plan on taking this point and shifting it up into 3 dimensions. Right? So right now we're just lying in the plane. We've got this point represented by an x-coordinate and a y-coordinate, and along a similar vein, we have it represented as a distance from the origin, r, and some angle in standard position, which we call theta. All right, so if we do want to take this idea and extend it up into 3 dimensions, let's go ahead and let's draw our z-axis. And now what we can do is we can take our point up some distance. Let's go ahead and maybe shift it along this vertical line segment here. Now I'm going to try my best to grab my point, but nothing else. Right? So now if I slide my point up here, perhaps do some strategic dragging and dropping over here. And I think I can go ahead and just close off that parenthesis. Here we go. All right. So now our point has an x-coordinate, a y-coordinate, and since we're now off the xy plane, it's also going to have a z-coordinate. Right? But if you think about our point in the polar representation, it still shares that same distance from the origin in the xy plane, and it still shares that angle from the positive x-axis. The only value that it has now that's a little different is it now has a z value. Right? So that's where this part of the definition comes from, where we say r theta is the polar representation of the projection of the point in the xy plane. So basically we're saying if we take our point of interest and project it down to the xy plane, r theta is that point in the xy plane. Okay, so this right here gives us our cylindrical representation of a point in 3 space. Right? So it's polar in 2 dimensions, in 3 dimensions it turns into cylindrical. Right? So how do we convert from cylindrical to rectangular? Well, our x-coordinate is going to be r cosine of theta. That comes from simple right triangle trig. Our y value is just going to be r sine of theta, again coming from simple right triangle trig. And then the z value is just going to remain the z value. So it's fairly straightforward for us to convert from cylindrical to rectangular. And on this slide, we see that the conversion from rectangular to cylindrical is very similar. If we're given coordinates in if we're given a point in rectangular coordinates, converting that point to cylindrical coordinates is fairly straightforward, right? It's going to rely on us to use a little bit of right triangle trig and to think of the right triangles, but once you get everything in the right place, it's going to be fairly easy for us to find our R value. It just comes from Pythagorean theorem. And our angle comes from understanding the way the tangent function works. And we typically don't define our angle as being something like arctangent or inverse tangent of y over x because of where we're at in space, in particular where we're at in the xy plane. Because our arctangent function only gives us angles between negative pi over 2 and pi over 2, and we might have an angle that's between, say, pi over 2 and 3 pi over 2. So we really have to look at the picture in order to determine the angle. All right, let's go ahead and try one of these out then. So in this example 36, we're asked to convert the point r theta z is equal to the point 4, 5 pi over 6, 3 into rectangular coordinates. All right, so what we're using here are the cylindrical to rectangular conversions. So let's go ahead and let's just state those again. I'll write these down at the top of the page. So if we're going from cylindrical to rectangular, x is just going to be r cosine of the angle theta, y is going to be r sine of the angle theta, and z is going to be equal to z. I think that's easy enough to see. So if we want to come up with the x value, x is going to be r cosine of the angle theta. Well, remember, r is the first coordinate, and theta is the second coordinate when we're representing points in cylindrical coordinates. So x is just going to be 4 times cosine of 5 pi over 6. And now we just have to think about what cosine of 5 pi over 6 is, but if we think back to the unit circle, we should know that cosine of 5 pi over 6 is going to be negative square root of 3 divided by 2. So cleaning this up a little bit, we'll be left with a negative 2 root 3. Right. Next, we want to find the y-coordinate of our point. Well, remember y is just r times sine of theta. Well, r again is 4, and the angle theta is 5 pi over 6. So we just have to remind ourselves that sine of 5 pi over 6 is 1/2. So this is going to be equal to 4 times 1/2, which is 2. So we've got the x-coordinate, we've got the y-coordinate. Should we feel so compelled, we could also write out the z-coordinate, but remember z is just equal to z. So z in this case is just going to be 3. So point points, we're going to point x, y, z is going to be equal to negative 2 root 3, 2, 3. So converting from cylindrical to rectangular, fairly straightforward. Don't really have to put too much thought or effort into that conversion. Example 37. Now we're looking to convert the point x, y, z equals the point 1 square root of 3, 2 from rectangular into cylindrical coordinates. So let's go ahead and start thinking through this conversion here. All right. In this case, since we're going from rectangular to cylindrical, it might be easiest if we start by actually plotting the point in a three-dimensional coordinate system, and then from there start thinking through our conversions. So let's draw our coordinate system and label our axes. Our point was the point 1 square root of 3, 2. So we'll come out 1 on the x-axis, we'll come out the square root of 3 on the y-axis, and then we'll go up 2 on the z-axis. So just for some reference, right about there is where I'm visualizing my point. Now I'll go ahead and I'll draw it a little bit thicker. Alright, so if we wanted to convert from rectangular to cylindrical coordinates, we have that r is equal to the square root of x squared plus y squared. So that's going to be the square root of 1 squared plus the square root of 3 squared, well, that's going to be the square root of 1 plus 3, which is the square root of 4, which is 2. So remember, what that value of 2 is, that value of 2 is the distance from the origin to the projection of the point down into the xy plane. All right. And just because I'm going to want to draw something else there in a second, I'm actually going to label this on the other side. So that is our R value. Right? The next thing we're looking for is we're looking for the angle theta. So remember, the angle theta stems off of the positive x-axis and comes over to this, I guess, line segment that exists in the xy plane. So a few things that we can think about here. We know that this distance is 1, and we know that this distance is going to be the square root of 3. So because we know those two distances, we can actually find theta in terms of our tangent function. So remember, tangent is going to be the side length opposite theta, which in this case is going to be the square root of 3, divided by the side length adjacent to theta, which in this case is going to be 1. So we're really trying to solve the equation tangent of theta equals the square root of 3. And because our angle is between 0 and 90, we could use the inverse tangent or arctangent function to solve for theta. But just thinking about it, we know that the angle theta should be the angle pi over 3. Or 60 degrees. So we've got our R value figured out, 2. We've got our angle figured out, is going to be pi over 3. And remember, when we're converting from rectangular to cylindrical or from cylindrical to rectangular, the z value just stays the z value. So we're also going to have that z is just equal to 2. Right. So combining these three key pieces of information, we can go ahead and we can state that the rectangular coordinates of our point are going to be 2, pi over 3, 2. Or sorry, not in rectangular, in cylindrical coordinates. All right, so there we have our point represented in cylindrical coordinates. The next thing we want to do is play around with this idea of surfaces in cylindrical coordinates. So very similar to how we can represent points in space in cylindrical coordinates, we can also represent surfaces in space by using cylindrical coordinates. So techniques for representing cylindrical surfaces surfaces in cylindrical coordinates are going to be presented in this next example. Okay, so let's go ahead and let's explore this a little bit. So in example 38, we're asked to find an equation in cylindrical coordinates for the surface represented by each of the two equations. So we have x squared plus y squared equals 9z squared, and then we have y squared equals x. So let's go ahead and let's start with this first one. So if we're trying to convert from rectangular to cylindrical, the first thing that I'm going to note here is that r squared is equal to x squared plus y squared, or r is the square root of x squared plus y squared. So by observing that, I know that I can replace this x squared plus y squared with an r squared. Right? And also, converting from cylindrical to rectangular or from rectangular to cylindrical, z stays the same. So I can just leave z as z. Now at this point, I can undo the r squared by taking the square root of both sides. And this leaves me with r is equal to plus or minus 3z. Okay, that's kind of an interesting thing to think about, but let's go ahead and maybe explore what this surface will give us. So if I do go ahead and I draw a three-dimensional coordinate system, I'll go ahead and appropriately label my axes. Now what we have is we have r is 3z. So think about what 3z is. Sorry, don't think about what 3z is. Think about what r is. R is the distance from the origin in your two-dimensional coordinate system. So for instance, when z is 0, this is basically going to be saying you have a surface whose radius is 0. It just happens to be right along the z-axis. But now as z increases, that radius is going to increase. So when z is 1, now you're coming out a distance of 1 around the z-axis. When z is something like 5, now you're coming out a distance of 5 around the z-axis. So if you were to draw all of these circles as you slide upwards, you would end up with a cone very similar to this shape here. And because the same is true for negative values of z, so for instance, if you were to plug in something like z equals -1, or z equals -2, or z equals -3, you would also have circles going downwards. So the graph of this shape here would just be two cones stacked on top of one another that intersect at the origin. So that is how we would draw or sketch the graph of our first surface. So our second one is y squared equals x. Let me go ahead and give myself a new page here so that we can sketch our second surface. All right. So this one gets to be a little bit trickier because we have to do a little bit of thinking beforehand, but we should be able to figure it out. Right? The first thing that I want to make myself a note of here is that y is equal to r sine of theta, and x is equal to r cosine of theta. So maybe these substitutions will be helpful, maybe they won't. So let's go ahead and let's replace the y with an r sine of theta. That'll leave me with an r squared sine of theta squared is going to be equal to x. Well, x is just r cosine of theta. Let's go ahead and manipulate this a little bit. Maybe we can divide both sides by r. And now we're left with r sine squared of theta is equal to cosine of theta. Again, probably a few more ways that we can go about manipulating something like this. Let's divide both sides by sine squared. Right. So, kind of another fun thing to think about here. Now that I'm looking at this, I'm not so sure if we're going to be able to this is actually something that we're not going to be able to graph. We could use a graphing utility or a graphing calculator, something like GeoGebra or the 3D calc plot, but by hand, we're probably not going to be able to graph this expression here. So since all we were asked to do was find an equation of the surface in cylindrical coordinates, we've essentially done that, and we could stop this problem right here. So with that, I'm going to go ahead and I'm going to leave this part of the video here. Remember, this is part 1 of a 2-part series. In this video, we looked at cylindrical coordinates. In the next video, we're going to look at spherical coordinates, which is definitely different than the extension from polar to cylindrical. Spherical is a little bit different. It's a little bit more complicated. It's a little bit more challenging to actually visualize what's happening. But like I said, I'm going to leave this one here. Go ahead and watch the next one, and then that'll be it for section 11.7. Thank you.